Let's look at some electron configurations. Okay, in the previous video, we looked at that interactive periodic table, looked at the electron configurations that happen. I want to kind of rehash some of those and point out some things that happen on the periodic table. So if we start with hydrogen, hydrogen has one electron. Excuse me. And that one electron is going to be in the 1s orbital. So we have, this is a 1 out in front there. And we have a superscript 1 representing that we have one electron. So this one electron is represented as that subscript. Helium has 2 electrons. It has an atomic number of 2, meaning there are 2 protons in that nucleus. For it to be charge neutral, we have to match the protons. We have 2 electrons. Its electron configuration is going to be 1s2. So again, this 2 is represented by the subscript number there. For lithium, okay, we're just adding an electron to each of these, so we have 3 electrons now. There's already a maximum amount of 2 electrons in that s orbital, so we can't add there. But we'll start there at least. We have the 1s2. Then our 3rd electron gets put in our next orbital up, so we have 2s1. Okay, then the 3 electrons there, they're going towards this 2 and that 1. For beryllium, we have an additional electron, 1s2, 2s2. Boron has 1 more electron than beryllium. We already have the maximum amount of electrons in that s orbital, so we go to our next shape, which is the p orbital. So boron has an electron configuration of 1s2, 2s2, 2p1. Then for carbon, nitrogen, oxygen, fluorine, and neon, we're just adding another electron in this p orbital here. And remember, there are 3 different orientations, 2 electrons apiece for a total of 6. So carbon's going to be 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. Neon, 1s2, 2s2, 2p6. Moving to the next element would be sodium. We're 1 more period down the periodic table, so we're going to increase our number. We're now going to go into the 3s. Sodium would have an electron configuration of 1s2, 2s2, 2p6, then we have 3s1. Now, you can imagine as we go further and further down the periodic table, our electron configurations get a little crowded. There's a lot happening. So we have a kind of a full version, a complete version here. We also have an abbreviated version. For the abbreviated version, we're going to take all of this other stuff that's represented by neon, and we're going to say, all right, this is now our new starting point. Okay, so we put the noble gas in square brackets, and that is our starting point. Okay, so this means 1s2, 2s2, 2p6. So what it allows us to do is it allows us to take this whole portion here and condense it down to much smaller. So we would say, rather than putting it here, put it on our original notes. Our complete version of sodium 1s2, 2s2, 2p6, 3s1. So what I'm doing is I'm taking all of that portion there and I'm going to abbreviate it with my noble gas. So everything there is represented by neon. Then our extra, that electron that we added, we just list out there. So magnesium here would become neon 3s2. Aluminum, we have neon 3s2, 3p1. We can fill these all in, right? We'd end with 3p1, 3p2, 3p4, 3p5, 3p6. I didn't count that right somehow. 3p2, 3p3, 3p4, 3p5, 3p6. Then this one here, so we have neon 3s2, 3p6. This configuration now gets condensed for the next row like that. So potassium, this now becomes just like argon. It's one further down the periodic table than sodium was, so we would increase our number by 1. And we have 4s1. Calcium would be argon 4s2. We talked about it in the video. Once we get to this row here, okay, we start doing transition metals. So this is kind of representing all of group B. And their number goes down. These are all D electrons, but their number is 1 less than what happened before. So we have, this is going to be the 3D, the 4D, and the 5D. Oh, 6D. So the d orbitals have 10 electrons. So once we move all the way across, these each would have 10 electrons there. So if, let's say we were going to do, this is arsenic. It's one of the examples we should do. Arsenic is just going to be just like argon. So it's going to have Ar. It's going to build and have the same thing as calcium, so 4s2. Then it's going to also have this 3d10. Then we have the 4p's, and we have 4p1, 4p2, 4p3. So if we look at this again, and looking at our complete version here, okay, we can build off of argon, which builds off of neon, or you can look at this complete order of our configuration. Okay, but arsenic needs to go until 4p3. So we're looking at right to there. So we need to write down all of these values and then 4p3. So our completed version, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. You remember that's that weird thing that happens. And then 4p3. To do the abbreviated version, okay, the abbreviated version takes all of the lower numbers and stops once you get to the first highest number. So 4 is the highest quantum number, so we stop right before there. And that gets abbreviated with that nearest noble gas. So it's argon, 4s2, 3d10, 4p3. All right. So let's kind of now, I want to correlate these electron configurations and how we see them from the periodic table. First thing to note that I've kind of been talking about is we have our period. Right, our periods are going down the periodic table. So hydrogen is in period 1, lithium is in period 2, sodium period 3, potassium period 4, 5, 6, 7. You'll notice then in this outer, or this electron that we add here, the period number matches that value. The number 3 matches there. Number 2 matches there. Remember, this group B, this doesn't really follow by the same rules, which is why, for the most part, we're going to try and ignore these here. They go one less. These down here, remember these two, these two rows get interjected here. We just pull them out usually. These would be the F orbitals, and they are one less than the D orbitals. Okay, so D orbitals here were 5. Down here would be 4. So that would be 4F and 5F. F orbitals can hold 14 electrons. So they'd be 4F14, 5F14. All right. Up top here, looking at our group A, our columns, right? We have 1A, and you'll notice that in each of these, we have 1 electron in the last orbital that we list. Group 2A, right, has 2 in that outermost, or that last orbital that we list. The group 3A does have 3 total electrons. You have to look at the total number of electrons with that highest quantum number, or look at the total electrons in the same quantum number as the period that it's in. So 4A, 2 plus 2, 5A, 6A, 7A, 8A. And you'll notice if you look at nitrogen and arsenic here, okay, nitrogen, when our quantum number matches the period number, we have that total number of electrons. So we have 2 and 3. Same thing down here for argon. Okay, we ignore the D ones because they don't have the same quantum number, but we have a 4s and a 4p. We have 2 and 3. So total of 5 there. So with your knowledge of how we've laid out the periodic table, go ahead and pause the video and attempt this Tellurium, TE, attempt looking at that complete electron configuration and the abbreviated one. All right, hopefully you have attempted Tellurium here for its complete electron configuration and the abbreviated one. I'm going to show the abbreviated one on this periodic table because we can use the periodic table to draw that out. Okay, and then on the other page of notes, I will write out the complete one when we can look at our list of all of the electron configurations. So the abbreviated electron configuration, we're going to move back to the nearest noble gas, which is krypton. So tellurium's going to start with krypton. Then we work across the row that our element is in. So we're going to have a quantum number of 5. First of all, we have the S, so we'll have 5s2, then 4d10, then we're working back in the 5 and the p's, so 5p1, 5p2, 5p3, 5p4. Just to check, in our highest quantum number, we have 2 electrons and 4 for a total of 6. We are in group 6A, so that is a good check for us that we've done our counting correct. To look at our complete electron configuration where we don't use this shortcut, we're using all the way up to the 5p4, so we're going to go all the way up to here. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p4. And again, our abbreviation is taking care of everything up to that highest quantum number. So all of this here is captivated by our abbreviated version using the noble gases. Then we would just have these listed of 5s2, 4d10, 5p4. All right, so in summary, you can memorize this. You don't really need to. We can use the periodic table to complete our electron configurations. Okay, the period number, our row number, that's the highest number that goes after the square brackets noble gas. Okay? Except for the group B, they get 1 less. The group number for group A, okay, ignore the d orbitals, total number of electrons that go after the noble gas. Okay, so if the group number is 6, for example, for tellurium, the total number of electrons in our highest quantum number have to add 6. So we have 2 plus 4 is 6. For group B, the quantum number is 1 less than the period number. The lanthanide and actinide series, those are 2 rows at the bottom, they are 2 less than the period, or 1 less than the d orbitals. We can also use the periodic table to remember how many electrons go in each orbital. So that's going back to our previous page of notes. The s orbitals can have 2 electrons, p can hold 6, d can hold 10, F can hold 14. The funky shape, right, this weird, not a block shape, but this funky shape, has to do with how many electrons can go in each orbital. We have 2 columns here. We have 1A and 2A. These are the s orbitals. Right? There's only 1 orbital, so it can hold 2 electrons. 1 electron, 2 electrons. Our p orbitals are over here. There are 3 p orbitals, so 6 total electrons. 1, 2, 3, 4, 5, 6. D orbitals are in the center here, group B. There are 10 electrons in the d orbitals. If you look on a periodic table and count how many columns you have. You'll notice that there are 10. F orbitals are in this, the outcropping here. There are 14 potential electrons that can be there. Count on your periodic table. You'll have 14 columns going across. There are 14 slots that you can put electrons there.